Good day, I'm Dr. T and welcome to my office. So today I'd like to talk a little bit about what we call nomenclature. Nomenclature is kind of a fancy word for naming. So how are we going to name those molecules and ions and whatnot? I'm going to basically stay away from alloys and let the metallurgist take care of those. So we're going to be looking at ionic compounds and covalent compounds. So let's start off by looking at some ionic compounds. Ionic compounds generally will focus around their empirical formula. Their empirical formula is the smallest whole number ratio of atoms. And because ionic compounds will always form a lattice, or if not a true lattice, if they're like an ionic liquid, it's still, general idea. There's no sense of trying to say the total number of cations and anions of each type, because there'll be trillions, or more, probably more. So instead we look at the empirical formula. Now, here's actually a rather interesting scenario. Those empirical formulas tend to be locked by the properties of the atom. If you have a bunch of cations and a bunch of anions, the charges are going to have to cancel out. The total number of protons between all of them has to equal the total number of electrons amongst all of them. You, once again, can have cations that have a deficit of electrons, but for every lacking electron you have in your cations, you have to have an extra electrons in your anions. Nature doesn't like charge. That's where you get lightning from, is having an unbalance of electrons. So you can always assume your ionic compound is going to be neutrally charged as a whole. This actually allows you to start predicting a few things. If you know the charge of your cation and anion, then you can figure out what ratio they're in, and thus the empirical formula. Now, this has a couple of consequences. For starters, when naming these things, I don't actually have to tell you the ratio. Some people might want to throw some numbers in the name, but no, we don't say numbers in the name. Instead, we simply tell you what compounds are there. We start with the cation, and I'm going to assume there's only two at the moment. There are definitely ways of naming larger compounds, but right now I'm just going to assume that there's a cation and an anion. We start with the name of the cation, and it's usually what you read off of the periodic table. So, yay. And the name of the anion follows that. And it usually is what you read off the periodic table, except for the last syllable. That is dropped and replaced by IDE, or IDE. Now, of course, if it's, say, oxygen, then the last syllable is -gen, so oxygen turns into oxide. But other ones like chlorine, it's the -ene, so the chlorine turns to chloride. This is simply telling you this is now an anion. So if I have a compound that contains sodium and chlorine, then I could call it sodium chloride. The reader would then be responsible for figuring out what the formula is. Okay, let's figure out what the formula is. If I have my two compounds, depending on where my elements are on the periodic table, then I can figure out, in some cases, what their charges are. If I have an alkaline metal, that's going to be that first column on the periodic table, those all have a charge of +1 when they're their ion form. They all had one valence electron, and they lost it. Poor ion. If it's an alkaline earth metal, that's group 2, those all had 2 valence electrons, and they lost it. I'll get back to the transition metals. Those are actually a tad bit more complicated, and actually down on the bottom of the P block with the true metals, I'll get to those here in a little bit as well, because those are equally as complicated as transition metals. If you're aluminum, I'd say that whole group, but really the aluminum is the only one that behaves in that group, then you have 3 valence electrons, and aluminum tends to lose them to form a +3 cation. The group with carbon doesn't tend to form anions or cations very well. It will occasionally, and they are insanely reactive little critters, what we call intermediates. Molecules that you can't actually collect in a bottle. They won't last long enough. They'll react. So, skipping over and looking at group, checking my periodic table to get the numbers right, 15, with nitrogen, these have 5 electrons in their valence shell. And in this case, they could lose all 5 to become a +5 cation, but truth be told, they actually would rather be an anion, so they typically gain 3 electrons. So nitride is going to be N3-. Next over, group 16, 6 electrons in their valence shell, so you do the math, goes up to 8, it's going to be plus 2 electrons or a negative 2 charge, because of course we had to give the electrons the negative charge. Boy, it would have been easier had they been positive, but they're not. Group 17, those are your halides. Those tend to be a minus 1 charge because they just need one more. And group 18, your noble gases, you're not making a compound out of those things. Oh, okay, xenon you can force into a molecule, but apart from that, you're not making a compound with these guys. So don't worry. They're just not doing anything. They're nobles. They're, noble gases. Now, from these charges, you can figure out what you have. So once again, let's say I have some table salt, some sodium chloride. I know I have a sodium that's a +1, and I know I have a chloride that's a -1. Oh, look, 1 to 1. This is going to work great. But what if I don't have sodium chloride? Let's say I have magnesium chloride. Oh, in that case, magnesium's +2. It's an alkaline earth metal. Chloride's -1, so how many chlorides am I going to need? You guessed it, 2. Yay. Now, there's actually a rather interesting trick here. If I take the charges of my 2 compounds, I can actually take the numbers, do a bit of a crisscross on them, and that's usually going to be the ratio that I need. I do have to be careful and check to make sure that, it's actually the smallest whole number ratio. If I had something like aluminum nitride, I might think that's Al3N3, but in reality it's just Aln. But yeah, there's my formula. This wasn't so bad. Okay, now to those pesky transition metals and the true metals, which is like most of your metals and like half the periodic table. The reason they're pesky, the reason these things get a bit annoying, is the fact that many of them, not all, but many of them are what we know as polyvalent. These are ones that will gladly form more than one different type of cation. Iron, for example, tends to prefer to form an iron 3+, but it will form iron 2+ quite readily. Okay, now we got a bit of a confusion. So we've got a couple of issues. One, if we've got a formula, we need to figure out which one we've got. And of course, in some compounds, you're going to have both, but as chemists, we're going to leave those to the geologists because those are usually minerals. So things like magnetite, both iron 3+ and iron 2+. Yay, not dealing with that. Moving on. Now, let's say I have iron chloride, but in this case, there's 2 iron chlorides. We've got the iron chloride with the Fe3+ and the iron chloride with the Fe2+. So I'm going to have this one, FeCl3. I know that this is the iron 3+ because there's 3 chlorides. The chlorides each have a negative charge. There's 3 of them, and the whole thing balances out to 0. Because remember, nature doesn't like charge. So my formula unit is going to have a neutral charge when it's all done. So this is iron 3+. How do I communicate that this guy is iron 3+? I have 2 ways. The newer way, which is definitely the simpler one, is to say iron, give it a space, parentheses, Roman numeral 3, close parentheses, and then continue with the rest of the name of the compound, in this case chloride. So I would say iron 3 chloride. Well, that was easy, wasn't it? Hi, this is me at my editing booth. So I realized I could have left a bit of a misconception in someone's brain. The 3 in Roman numerals coming after the iron, or really the Roman numerals themselves, represent the charge on the cation, not the number of anions present. So for FeCl3, that's iron 3 chloride, but you would also have iron 3 nitride if it was Fen, even though there's only one N because the Roman numerals correspond to the charge, not the number of anions. There is an older way, which is definitely more poetic, but harder to use, and as much as I like the old ways, it's probably time to go away. But it's not, so we're going to have to learn it. The older way starts by naming iron in Latin. Yeah, Latin. So iron's name is ferrum, which is where the Fe comes from. And we're going to drop the from it. So ferrum is telling you that it's metallic iron. But I'm going to drop the And I'm going to put one of 2 suffixes at the end. Ic if the charge on my cation is the higher of the two, because most of these polyvalent ions only usually like to form two different cations. They don't get all fancy in like 3 or 4. So usually it's only 2. So ic is going to end up indicating the higher of the two. And for iron, if you remember, there was a 3 or a 2, and 3 would be the higher of the two. So ferric would say it's iron 3+, where ferrous would indicate the lower of the two. So the us ending indicates the lower, and so that would be iron 2+. Now here's the part that confuses students. The ic and the us are relative. If I'm dealing with copper, copper forms 2 cations, 2+ and 1+. Copper 2+ is cupric, because it's the higher of the two. Copper 1+ is cuprous, because it's the lower of the two. The actual number doesn't matter. It's the relative position relative to the other cation that is important. So for example of FeCl3, I could call it iron 3 chloride, or I could call it ferric chloride. You'll quite often still see ferric chloride used, so you do need to be able to switch between these two and know which one to call it, because you will see it in both ways. Now, just before you think that the metals are having all of the crazy times, we need to look at the nonmetals. Nonmetals like to form molecules, and molecules can be in excess of electrons, or in deficit of them, what we call polyatomic ions. These are discrete clumps of atoms bound together with covalent bonds, but as a clump are either in excess or in deficit of electrons. They have a charge to them. Most of the polyvalent ions that we are going to deal with are anions, although I should point out that ammonium, NH4+, is definitely something you're going to run into a few times. The way we deal with these is basically the way you would deal with any cation or anion, except for a couple of interesting quirks. Ammonium is just ammonium, and you'd use it like it's a metal, even though it's not. But the anions, you're not going to drop the last syllable. The last syllable is actually probably already taken, so they're not going to end in "ide." This is actually a telltale sign that you have a polyvalent anion from the name, in that it doesn't end in "ide." Many of our polyvalent anions are what is called oxyanions. In this case, you're going to have some element, usually a nonmetal, well, not usually, it's going to be a nonmetal, and it's going to be surrounded by oxygens. So we could have something like sulfur surrounded by, say, 4 oxygens. And in this case, we're going to end it in ate, A-T-E. Now, I actually should say that this is a slightly complicated scenario, because the ending of ate applies to the kind of the normal one, or the most common, even though it may not actually be the most common. The ate isn't the only game in town. SO4 2- is a polyatomic ion, sulfate, but it's not the only polyatomic ion involving sulfur. In fact, I can just as easily have SO3 2-, short 1 oxygen. And in that case, it's not going to have the ATE suffix, it's going to have the ITE, or ite suffix, sulfite. There's a few patterns on the periodic table as far as which ones get ate, ite, and that kind of thing. There are about as many patterns as there are actual elements. They're ones you almost definitely get to memorize. Sulfur and phosphorus, the 8 is going to be O4. Ite is always going to be 1 less than 8. So you don't need to memorize both the 8 and the ite. That's kind of pointless. Once you got one, you're good. Now, that's all those two form. Carbon and nitrogen, similar story, just instead of O4, it's going to be O3. So the 8 for carbonate is O3. That's all you get for carbon. For nitrogen, it's going to be O3 as well. That's going to, once again, be 8. Ite would be O2 kind of scenario. Now, those halogens. The halogens are going to form their 8 as the O3. So chlorate would be ClO3, bromate would be BrO3. The reason why is that for the halogens, you actually get between 0 and 4 oxygens. There's no lower limit. So you can have ClO4, ClO3, ClO2, ClO, well, there's no 1, but just ClO, and then Cl. Of course, Cl is ide. ClO3, as I just mentioned, is 8, and ClO2 would be 1 less than the 8, so it's an ite. What about the other two? Okay, above the 8. So if whatever you're calling 8, and it depends on what your core atom is, that's going to be called the fill in the name of the atom, 8. So for ClO4, that's going to be called perchlorate. Actually should sound familiar. You do hear about perchlorates as pollutants or things on Mars on a somewhat irregular basis, but you do occasionally hear of them. Now, how about the ClO, the one below the ite? So if less than the ite isn't the ide, if there's a gap, it still has an oxygen, then we call that hypo, whatever the name of the core atom is, ite. So this would be hypochlorite. With that said, have a wonderful day.